Our next lightning talk, and Lars is going to be talking to us about dependent types.
Right.
So welcome.
Hi. So I'm Lars. I'm a mathematician, but I work as a Haskell developer for IOHK. We build blockchains and cryptocurrencies, and we are hiring. So if anybody's interested, please visit our website. But my talk has nothing to do with that. I mean, that's a private project I've been pursuing for 15 years or so. And the idea is to somehow model mathematics, and you can, of course, do that with dependent types, like in Coq, in a computational way. So actually, you get something. If you prove a theorem, you can actually run it and convert it into code. But for a mathematician like myself, it's somehow unusual to use all this type theory, because classically, mathematicians use set theory. And for example, you have set comprehension. Means you can define new sets in terms of existing sets by giving a property that the elements of the new sets are supposed to have. And that's awkward to do that like in Coq. I mean, you can, but then you need these sigma sums and so on. So it would be nice if we could do that somehow in a more natural way, natural for mathematicians. And the idea is, I mean, set theory, one way to characterize that in a categorical way is using Topoi, the concept of a topos. So a topos, an elementary topos, is a category with certain properties. And if you have such a topos, then a lot of the things you can do in set theory, you can do in that category. So for example, you could construct something like the reals and do calculus and so on in any elementary topos. Right, so I'll try to briefly explain what it is. So elementary topos is a category that has finite limits, exponentials, and sub-object classifier. The latter is the most important one and the most interesting one. So the finite limit thing just means it has a terminal object, finite products, and equalizers. And exponentials is function objects and the sub-object classifier. Equalizer is not so important, but just for those who don't know it, so you have two objects, x and y, and two morphisms from x to y. And the equalizer is basically the set. I mean, in sets, it would be the set of elements of x that agree for those f and g give the same value. So in sets, it would just be defined by a comprehension like this down there. Right, and as I said, the most important concept in a topos is this sub-object classifiers. So, and what is that? It's so if you have a terminal object star, then the object omega is called a sub-object classifier. It comes with a morphism embedding from this terminal object into omega, and this is the universal sub-object, so the universal injective map, basically. And that means if you have any sub-object y to x, m, then there is a unique characteristic morphism, this chi m, from x to omega, that classifies this sub-object in the sense that the square becomes a pullback square. So that means if you have any morphism into x, that makes the whole outer thing commutative, then you get an induced morphism into y. And in sets, this omega is just a two-element set. For example, we can think of it as the element of Booleans, true and false. And true is then just the mapping of the singleton set true into, I mean, mapping true to true. And this characteristic map chi is just the map that maps all elements in x that come from a y to true and all others to false. Okay. Right, and that is closely related to the comprehension axiom, because I mean, then you can basically define this y in terms of this chi, and so once you have this sub-object classifier, you basically have comprehension. Okay. And in sets, I mean, the prime example of a topos is, of course, the category of sets. So I already basically explained, I mean, singleton, I mean, the terminal object is just a singleton set. Product is just a Cartesian product. Equalizers I already showed on the other slide, so you can just write it like this. Exponentials is just a set of functions, and any two-element set will do as a sub-object classifier for example, we can imagine the Booleans with true and false. And if you take a typical category that arises in functional programming, like Hask, objects are Haskell types and morphisms are total functions, then some of these properties are there. I mean, we have a terminal object, just the unit type. We have products, that's pairs. We don't have equalizers. We do have exponentials, just functions from A to B. And we crucially don't have a sub-object classifier. Yes? Okay. Yes. And one more thing to make it more interesting. If you just take the category with one object and one morphism, that would be a topos. But of course, that's boring. So in addition to wanting a topos, I want a topos with a so-called natural number object, which basically means you have primitive accursion. So you have an object n and morphism 0 and successor. That is universal. So if you have any x and some point in x and a s from x to x, then you get a unique map from this natural number objects into x. Right, so that's the topos and natural number object. So now what do I want to do? I want to basically, I mean, you can write down there are finitely many axioms of these elementary topoi, and you can just write them down syntactically, and so you can use them according to the axioms of a topos to construct objects and morphisms. And those objects and morphisms would then basically have an interpretation in any topos, for example, in sets. But in addition to that, I also want to interpret that so that I basically, if I get a morphism, I can compile it and actually run it. And so the question is how to do that. And if one could do that, then, I mean, you can do in principle mathematics and then also in a computational way. And the problem is, if you look at the sub-object classifier thing in this specific example, so you have the successor function on natural numbers, and this gives a characteristic, this indicator function, which is basically greater 0. And for example, the number 42 makes this diagram commute because 42 is greater than 0. So by the axiom, this red arrow must exist, and that must map 42 to 41, the pre-image of 42 under successor. And so if we want that in a computational way, then somehow the interpreter of the model, given this 42 and the proof that this diagram commutes, must produce the 41. So somehow it must come up with the predecessor. And so that's the main problem. We also don't have equalizers normally, but that's not such a big problem. That's more like an additional check. So you could just ignore the proofs in the end, and it would still run. You just give up some guarantees. So I mean, the biggest problem is how to deal with these sub-object classifiers. Right, and the key idea is that, I mean, in order to prove that such a diagram exists, somehow in this proof, I mean, how do you prove that 42 is a successor? I mean, somewhere in your proof, probably you need the 41 to make that proof. So the key idea is to somehow track this information, track the proofs, take them, I mean, make them first class, and then use the information contained in the proofs to actually construct this 41 when you need it. And so basically this is now the model. So instead of just using types, the idea is to use what I call setoids. That's just a Haskell type, but it has an associated type, proofs A, so type A with proofs A. And the idea is that a proof A, an element of a proof A, is an explicit version of proving that two elements of A are the same. And then I want some axioms like reflexivity, symmetry, transitivity. So if I have a point, then I always get a proof that the point equals to itself. If I have a proof that 2 points are equal, then I also get a proof in the other direction. And if I have 2 proofs composable, then P equals Q and Q equals R. I mean, yes, then I can compose those proofs. So I have these explicit proofs. I have a type and a type of explicit proofs that 2 elements are the same. And then on things like that, I can also define functions. So what's a function? It's just a normal function on the points, but it must also send proofs to proofs. So if I have 2 points that are the same, x and x prime, then this function must transform those 2 points into points that are again the same. So it's additional data. I don't just need the mapping on points. I also need such a mapping on proofs. Right. And then in my model of the topos. An object is just something that basically has no information except it knows the underlying points, this setoid. A morphism is just something that has a source and a target, which are objects, and then a function on domains, right? So I showed that before. So this is such a it's a function on points, but it also maps proofs accordingly. And finally, I have a third category of things, proofs. So maybe the picture is better. So if I have two objects and two morphisms with the same source and target, then I want to have an explicit proof that those two morphisms are the same. And what that does is just for each point in the codomain, it produces a proof that the result of the first function equals the result of the second function. Okay, now, yes, so this is now the most important idea, how to do these these omega points. So what is an omega point? Basically the Booleans in a constructive way. So that's just a pair of a function and a point in the domain, in the image space. And when are two such equal, if I have something in Y that maps to a point down there, and I have a proof that those 2 points are equal. And something like that, when are two such things equal, if I can map such a small y to a y prime and the other way around. And the point of this is the true is a trivial thing. It's just the identity of star. And star, so I always have a point in true. So if I have such a proof, then I can look at the image of star under this red arrow and get an actual element y. And that is then basically my 41 in the example. So, and then of course you need to do these things for all other things like products and so on, but that's all easy. That's the most interesting part. That's it. Thank you.